So our first task is going to be to figure out how to generalize the idea of the tangent line to the graph of a single variable function into a multivariable setting where we want to find an equation for a tangent plane to the surface, which represents the graph of a two-variable function, for example. So as in our introduction, right, the idea is that if I can find an equation, maybe a parameterization, if we like, for a line tangent to my surface in the x direction and the line tangent to the surface in the y direction, then those two lines both need to be contained inside of my tangent plane, and my tangent plane needs to pass through the point of tangency that we're interested in. And so once we know a point and we know a normal vector for a plane, we can use those two pieces of information to determine an equation for that plane. So finding a point for the tangent plane is not challenging because we already know what point we want to have this tangent plane touch my surface at. And so it's finding that normal vector, that direction which is perpendicular to my tangent plane. In other words, it's going to be perpendicular to both of these tangent lines in the x direction and the y direction. That's going to be the interesting question for us in this preview activity. So in the preview, we sort of step through this in a few different steps. And we begin by thinking about this function. F of x and y is 6 minus half x squared minus y squared. And its graph is sort of this upside down parachute looking thing. It's an elliptical paraboloid, if you like terminology, and I usually do. And we want to try to find an equation for its tangent plane at the point where x is equal to 1 and y is equal to 1. So our first task is just going to be to kind of understand what this point is, right? The point on the surface that is going to be our point of tangency, the place where my tangent plane touches this surface. So that's going to be step one, is just to find coordinates for that point. And evaluate the partial derivatives, just so that we have those partial derivatives at our fingertips. And then we're going to sort of rewind the tape to yesterday and once again think about those partial derivatives as slopes of tangent lines to traces of my graph in the x direction and the y direction respectively. And once we've done that, we're then going to try to take those two-dimensional pictures and resituate them inside of 3 dimensions so that we can try to figure out what 3-dimensional direction vectors are going to be parallel to the tangent lines that are determined to the surface in the x direction and the y direction. So that's kind of the roadmap for how we're going to get started on this set of activities. So let's get started with you in your teams on just part A and part B. Finding the values of the function and its partial derivatives at the point in question, and then finding sort of what point needs to be contained inside of our tangent plane before we start trying to figure out what orientation that tangent plane should have by looking for a normal vector. So let's start by finding that point and its partial derivatives in parts A and B. So far, what we know about a tangent plane to the graph that we're looking for is we know what point that we want this tangent plane to pass through. Because we know that we're interested in the tangent plane at the point where x and y are both equal to 1. We need a z-coordinate on that point as well. And remembering that the graph of a function f of x and y has the z-coordinate equal to f applied to the x and y coordinates, that makes the coordinate of our point, I'm going to call this point P, if you don't mind, group 2, that have x and y coordinates of 1, and the z-coordinate is 4.5. And we knew that because 4.5 was f of 1, 1, right? So all you did was evaluate the function f of x and y for x equals 1 and y equals 1. So 6 minus 1/2 minus 1, that gives you 4.5. Right? So here is the point that we need to make sure that our tangent plane passes through. And we'd like to be able to use these partial derivatives as a way to determine what orientation that tangent plane has within space. So that's the tricky part. That's the part that we're going to have to do some work to figure out how to do that. So the way that we'll start is, again, rewinding the tape to yesterday and putting those tangent lines of the traces of our graph back into context. So you figured out that the x direction partial derivative was equal to -1, and the y direction partial derivative was equal to -2. And that shows up in the traces of our graph, which you can see over here as the slopes of those tangent lines. So when I take a slice of this graph at a constant value of y, so if I set y equal to 1 and let only x vary, then the slope of this tangent line at the point x equals 1 is going to be the x partial derivative, and so that slope should be equal to the x partial derivative that you found in part A. And sure enough, when you look at this green tangent line, it does have a slope of -1. Similarly, if I let x be a constant, so if I put a 1 in for x and let only y vary, then the slope of the tangent line at the point y equals 1 here is going to be the y partial derivative. And sure enough, the y partial derivative value, -2, looks like it agrees with the slope of this orange tangent line that we get in the trace at a constant value of x. And so the next task here is going to be to figure out how to come up with, first of all, well, do we even want to do part D? I actually kind of want to skip part D. Let's skip over part D. Rather than find an equation for each of these tangent lines, and that's just sort of a single variable, it's almost an algebra exercise, right? Because we want to care not about the equations of these tangent lines in two-dimensional space. Ultimately, we want to figure out how to find equations for the tangent lines in three-dimensional space that are tangent to the surface. So we need to start climbing that mountain here. And so to do that, what I want us to do is kind of look at those diagrams, those traces again, and instead of thinking about finding an equation for these tangent lines, let's try and find direction vectors for these tangent lines. So on these pictures here, I've sketched a little purple vector, which we can think of as a direction vector for the tangent line in the x direction, and a little red vector here on this diagram, which is a direction vector for the tangent line in the y direction. So let's do part E in groups. See if you can figure out what should be the components of this purple direction vector for the tangent line in the x direction if the x component of that tangent vector is equal to 1. So that's part E. And then in part F, you'll do the same thing, but for the y direction. Right? If the direction vector there has a y component of 1, if you like, then what should the other component of that direction vector be? So you're going to find components, so coordinates, if you like, for this purple tangent vector and for this reddish tangent vector here in parts E and F. And once we have those, the next step after that is going to be to try to bring that into three-dimensional space. But let's do the two-dimensional direction vectors first, and then we can move forward from there. So tricky part 1 was figuring out how to take our knowledge of slope for these lines and turn that into a direction vector that's parallel to each of these lines. And ultimately, the way that we figured this out, right, was that a direction vector for one of these lines should be sort of telling us that the x and the y components of that direction vector should correspond to a rise and a run, respectively, along this line, right? Because that's how we get from one point on this line to another point, is we add some multiple of the direction vector. And so the direction vector, the y component and the x component of the direction vector need to stand in the same ratio as the rise stands to the run. In other words, they need to stand in the ratio that's equal to the slope. So a line with a slope of -1 needs to have a direction vector whose y component is -1 times as much as its x component. So if the x component is 1, the y component would need to be -1. And my tangent line over here, which has a slope of -2, if its x component is 1, then its y component would have to be -2. So keep in mind here that sort of the way that I wrote these parts E and F, I've already put the number 1 into the x components of these vectors just to make it convenient, just so that we can spot, I'm going to sort of highlight this here, we can spot the x partial derivative and the y partial derivative values when they pop up a little bit later on. But of course, we could also have used any multiple of this v sub x if we wanted to. You know, I don't know, -8 comma 8, or 19 comma -19, right? Any one of those direction vectors would still be a valid direction vector for that line with a slope of -1. But using an x component of 1 is going to make it easier to figure out what the partial derivatives have to do with our ultimate answer. So this part was a little tricky because it forced us to go from slope to direction vector. The next part is also a little bit tricky, but in a slightly different way. What we want to do is take both of these pictures. Each of these pictures arose from a slice, a trace of the graph of our function in the plane y equals 1 and in the plane x equals 1, respectively. The next job is going to be to take those two pictures and put them back into the three-dimensional context to figure out equations for these tangent lines as they sit within 3 space, or at least find direction vectors for these tangent lines as they sit within 3 space. And so here's the actual picture, and I've kept the color coding from these graphs, so the red trace and the green tangent line, the blue trace and the orange tangent line, all those colors are the same on this diagram. So here is my red trace, which is the trace in the x direction at a constant value of y equals 1, the green tangent line, and a three-dimensional direction vector to that tangent line, which I'm calling u sub x. And then the blue trace, which is a trace in the y direction at a constant value of x equals 1, and the orange tangent line to that, and a direction vector in 3 space to that tangent line, calling it u sub y. There is a GeoGebra link you can use here if you want to spin around that picture and see it from whatever angles that you would like, and I do recommend doing that. And so the job now is going to be to figure out, using your coordinates from your two-dimensional direction vectors from before, see if you can figure out coordinates for these direction vectors as they reside within 3 space. And the hint that I give you here is that you should try to use the fact that each one of these direction vectors resides entirely within a vertical plane. So u sub x, for example, resides in a plane in which the value of y is constant. The value of y is not changing. So that direction vector should not point in a direction along which it is possible for the y value to change. Similarly, for the u sub y direction vector, it resides entirely within a plane where the value of x is constant, and so it should not point in any direction that has the potential to change the value of x. So you now need to come up with all 3 components of the direction vectors ux and uy by thinking in that 3-dimensional context and using the coordinates of your 2-dimensional direction vectors that you just found previously. Putting your 2-dimensional slopes, your 2-dimensional direction vectors into the 3-dimensional context was a little bit tricky at first, right? Because it, again, required us to think about vectors as directions having an initial point rather than as points, right? But in order to do that, you were able to take this picture, for example, and spin it so that we are looking at the original 2-dimensional picture that we had, right? So we're looking here at the xz plane, so we're looking down from the positive y-axis. And the slope of this green line was -1, but that's a slope in the xz plane. And so our direction vector in 3 dimensions should have an x and a z component that reflect that slope, but should have a y component which reflects the fact that this picture resides entirely within a plane in which the value of y is being held constant. The value of y is equal to 1 at all of these points in 3 dimensions. And so the direction vector that we use, u sub x, to represent this tangent line should point in a direction along which y does not change. And so the y component of that direction vector can be taken to be 0. And so you figured out that this direction vector can be taken to be 1, 0, -1, because -1 was the slope in the xz plane given by the x partial derivative. And so the same thing that worked for the x direction also works for the y direction. If we just turn our picture around so that we're seeing the yz plane, and we can see the slope of that orange tangent line right there was -2. But now, since we're looking at the yz plane, it's the y and z components of the direction vector which need to stand in that ratio of -2 to 1. And the x component, because this picture is entirely resident within a plane in which the value of x is being held constant, x equals 1, the x component of that direction vector should be set to 0, so that we don't leave the plane x equals 1 if we travel along that direction vector. And so the direction vectors that you found here for those 2 tangent lines can be taken to be 1, 0, -1 and 0, 1, -2. Right? So the 1, 0 here being sort of the clue that this direction vector is pointing in the x direction but not in the y direction. And 0, 1 in this one tells us that this direction vector is pointing in the y direction and not at all in the x direction. And the z components, again, these are these numbers that we're sort of carrying with us through all of these calculations. These numbers happen to be exactly, respectively, the x and y partial derivatives that we computed at the very first step of this problem. So now we're going to bring it home. So use all this information to find an equation for the plane which passes through the point that you found and which contains both of the tangent lines. In other words, that plane needs to be parallel to both of these vectors that you found in the previous part. So let's find an equation for that plane, and that's how we're going to wrap up this preview. This is the hard work for today. Once we're done with this, it's going to be smooth sailing for the rest of this section. All right, so once we knew what two directions we needed to be parallel to my plane, in other words, both of these direction vectors for my tangent lines, we could find a normal vector to the tangent plane by taking the cross product of those two directions, because the cross product of two vectors is perpendicular to both of the vectors that were crossed. So you took the cross product, you figured out that that was 1, 2, 1. And then you could use the ye olde equation for a plane template, right, to discover an equation for the plane, so that the components of that normal vector become the coefficients of x, y, and z. And then by evaluating the resulting expression at the point in question, you can figure out what the right-hand side of that equation needs to be. And so you ended up with this equation, x plus 2y plus z is equal to 7.5. So that's an equation for the tangent plane. What I would recommend doing, so I want to sort of give you a little bit of a hand in taking this last step. Let's do this. So I want to put the coefficient of 1 in front of this x, just for no particular reason. And I'm also interested in, let's see. So you did some arithmetic to get this 7.5. I kind of want to hit the rewind button on the arithmetic that you likely did, and sort of turn this equation back into the sort of the point slope type of version that we sort of have in our equation for a plane. In other words, what I want to do is just kind of rewrite this as x minus 1, 2 times y minus 1, and 1 times z minus 4.5, and then a 0 over here on the right-hand side. Right? So this might have been the format in which we wrote this plane equation sort of to begin with. And so the last thing I want us to do together is to kind of figure out what is the general principle. So what do each of the pieces, so each of the numbers in this equation actually stand for? So let's take 5 minutes or so for you to speculate on that, so that we can sort of earn for the day a general principle for how to find the tangent plane. After we rearrange this equation for the tangent plane, we can find the partial derivatives, the -1 and -2 that we've been sort of interpreting in a variety of different contexts along the way. Those partial derivatives pop out right here as the coefficients in the sort of point slope formulation of this equation, right? That -1 is the coefficient of x minus 1, -2 is the coefficient of y minus 1. And so these ones are the x and y coordinates of the point that we're interested in finding the tangent plane at on our surface. And then this 4.5 here was the z value of that point. So it's f of the x naught and y naught, the point that we're trying to find a tangent plane for. And so if we abstract this all out, we find that an equation for a tangent plane to the graph z equals f of x and y can be given by z equals f of x naught comma y naught. So that's that 4.5 that comes at the beginning here, x naught, y naught. So the z coordinate of the point on the surface that we're looking at. And then we're going to add the x partial derivative at the point in question. So that's my -1, multiplied by x minus the x coordinate of the point in question. And then also add the y partial derivative, again, at the point in question. So x naught, multiplied by y minus the y coordinate of the point in question. into our document here. And then that is going to be kind of our general principle, if you like, right? So an equation for a tangent plane to the graph z equals f of x and y would look like this, right? Z is equal to f at the point in question, so the z coordinate at the point in question, added to the x partial derivative times the difference between x and x naught, added to the y partial derivative times the difference between y and y naught. So there is kind of our general principle for how we can find an equation for a tangent plane to a surface. I want to put a border around that, but I don't know if Google knows how to do that for me. What if I do this? Hey, there we go. Not the greatest looking, but you get the idea. So now we know how to find an equation for a tangent plane to a graph of a surface. This same idea is also going to let us linearize a function. So this gives us a way of approximating the value of a function f of x and y near a point at which we know the value. So near a point x naught, y naught, we can use this tangent plane as an approximation to the value of the function. So that's what we're going to do in our next activity. And then from that idea of linearization, we're going to bootstrap our way up into the multivariable chain rule. So that's the roadmap for where we're going to go once we move off of the idea of tangent planes.